Okay, so we're looking at exponential and logarithmic graphs with absolute values. I thought I'd start with a little recap of how absolute values work again, and remind you that all it is a measurement of the absolute distance from 0. So if I was to take the absolute value of 3, then I'm finding the distance between 0 and 3. So in this case, it is actually a length of 3 units. If I look at the absolute value of -4, then it would look at the actual distance between -4 and 0. In this case, it is 4 units. Now, the simple way of thinking about it is, if the stuff inside the straight brackets, or the absolute value brackets, is positive in the first place, you keep it as the same thing. If the stuff inside the absolute value brackets is negative, then you have to unnegative it, or in simple terms, multiply what was inside the bracket by a -1. So when we have funny things like x's, what you end up saying is there will be two cases. If x was already positive, like the 3, then you keep it as the same thing as the x, provided that x is positive. Remember, 3 was positive, so you kept it the same. So x is positive, keep it the same. When it's the opposite scenario, when the number in the bracket was negative to start with, we multiply it by a -1 to get the positive version. So in other words, we write it's equal to -x if x is less than 0, or if x is negative, in other words. And we put in that little equals there to make sure that we cover the equals case when x equals 0. Now just one other one, if I have anything inside that straight bracket, we can split it up into two pairs of scenarios. Scenario number 1 is where the stuff inside the straight bracket is actually positive to start with. That means you keep it the same. If that thing was greater than or equal to 0. And the second scenario is if that was negative in the first place, then you have to multiply all of this by a -1. So we can say -1 times 2x minus 1 in the scenario that 2x take away 1 was negative. Now obviously there will be requirements of rearranging this section of the limits so that x is actually some sort of interval, but I'm going to leave that for now because that's actually less important. But for the purists, here's what you should get. You should get x is greater than or equal to 1/2 in the first case, and in the second case, the opposite scenario, x is less than 1/2. So on to exponential graphs with absolute values. So what we look at is writing this initial equation as the two separate areas. So you will have the scenario where x was positive, and that's when we keep the x as x over here as the index. The second scenario is where x is negative, in which case we multiply this number by a -1. So when we draw this graph, you'll actually have two parts to it. I knew I should. Okay. So we've got the x and y value axes as usual, and if I color code these, if I make the bit on the right the positive case, forgot to make the little line there for the equals scenario, then it's going to be in a shape that's exponential like so, except we only use this part of the graph. There we go. And it will have a y-intercept only, and it will be 0, 1. Now, if you like, you can put this in as a bit of more accurate detail, perhaps to explain what's going on. And so if you do that, then you need to write in the y asymptote, the horizontal asymptote. If we then color code the left hand side with, let's say, the purpley color, then this part of the graph will look like a reflected e to the x curve, reflected about the y-axis. So if that's the mirror, you get this shape over here. But you only pick the left hand side values of the x-axis, so we only have to draw in that part there. So you have this part here, and if you want it to be complete, then the rest of it would have been that dotted version. Now the second scenario, y is the absolute value of e to the x, is actually a lot easier than you expect, because e to the x is positive for all x values. So this graph is actually the same as this graph here. So if I was to draw the basic graph on the right here, y and x, then your basic e to the x graph is shaped like this, and because it's always positive in the first place, then your final e to the x graph with the absolute value is actually the same. So I wrote that all funny, but I hope you get the idea. So now let's look at the logarithmic graphs with absolute values. Again, we can write that in two parts. We can have the first part, which is where x is positive. So you keep everything the same for the case that x is greater than or equal to 0. Actually, you're not allowed to have that, so I should just change that to x is greater than 0. And the second scenario is where it's negative. So we would take the internal part of that bracket and multiply it by -1. Now if we draw this on a graph, then what you have is the basic usual y and x-axis, and our basic graph of log e to the x itself has a vertical asymptote of x equals 0, and it has a shape like a banana going that way, and we'll have a x-intercept of 1, 0. Now the reflected version would be looking at this reflected in horizontally, so that means it's reflected with this as the mirror line, so it's going to look like this. So if we draw that in, you'll have this shape here, and you have the x-intercept at -1, 0. Now here's a second scenario where you have the absolute value of all of, this is the log e there. You're taking the absolute value of the whole thing. Now the easiest way of doing this is to actually have the original sketch of what's in the actual bracket in the first place. So if I draw that over here, then the basic graph, let's color code it with orange, of log e of x is the banana shape going like this through here with a vertical asymptote of x equals 0, and it looks something like this, 1, 0 here. Now, knowing what we know about the absolute value, it means that you keep whatever is positive, positive, and you invert whatever is negative, so that it's the -1 times that final value. So on this part here, it's positive in the first place, so we keep it as it is. And so we would write for this part log to the base e of x if x is greater than 1. And we would draw that in blue over here, like that. For the other part, it's where the graph is negative, which is between 0 and 1 in the x values. So we write that as negative log e of x, where 0 is less than x is less than 1. And it's not defined anywhere else. There's no possible values of this graph for x is less than 0. So to draw the final bit in, you'd take the reflection of this part and put it up here. So that will look like this, roughly. It'll still have the same x-intercept. Now, there is an alternative way of finding the rule and the inversion and all that sort of stuff for the second case. So let's say you blindly applied the rule where you could split that into two parts. You've got the positive case, where log to the base e of x was positive, and the negative case, where, oh, that's a big x, sorry, the log to the base e of x is negative. If we were to rewrite this part of the equation over here, that would be log to the base e of x is greater than or equal to 0, and so you can make everything to the power of e on both sides, which means you get rid of the log on this side to get x is greater than or equal to e to the 0, and in case you forgot, anything to the power of 0 equals 1. So this is a case where x is greater than or equal to 1. The second scenario here, you can rewrite as log to the base e of x is less than 0. And again, the same algebraic tricks apply. So you'd still get x is less than e to the power of 0, and so therefore x is less than 1. But you would have to recognize that we have to assume that this number here is greater than 0 for this to work. So therefore you have to actually know the second part here, that x is greater than 0, which is additional to what's actually in the equation. So here's one where you have an absolute value and another absolute value within that. And so what I do is actually split it into just drawing that first and then finding the absolute value later. So here's the sketch. Y-axis and x-axis. Now, this basic graph in here is actually the log graph on the right and the log graph reversed on the left, with intercepts of 1, 0, negative 1, 0, and a asymptote in the middle of x equaling 0. So we can split that up into the sections. In this case, there are at least 3 sections. There's this section here, there's this section here, and the third section would be in between here and here, but because that's an asymptote, I can split that into 2 separate bits. So the convention is to write the positives first and then work your way downwards in the x values. So the first one is log to the base e of the absolute value of x, where x is greater than 1. And I'll include the equals sign in there. So that will be this line over here. Okay? Excuse the drawing. The next section is the negative section under here, and that gets reversed up to there, or reflected up to there. So I'll draw that in purple. And if I write that in as the rule, we have negative log to the base e of x, where x lies between 0 and 1. The next section is another purple section, where you're looking at this negative region in here. And so that gets reflected up here as well. So we draw that in. And there's still a asymptote of x equals 0. So the other scenario you could have is the same rule, but x is between 0 and negative 1. And we usually write the smaller number on the left. The last section is the positive over here, and it's the case where x is less than negative 1. So once again, I'll draw it in blue, And the rule for that is, now we need to make that bigger, log e to the base e of x, where x is less than or equal to -1. So here are some general principles. 1, you have to consider the basic graph you've got. 2, you can apply transformations. 3, find the y-intercept by substituting x equals 0. And 4, find the x-intercept by letting y equal 0 and then solving for x. So here's an example. Let's say we need to sketch the graph of 2 times log to the base e of the absolute value of x plus 2, and then take away 3 from that. So here's the general form of that graph, and hopefully you have remembered from before that this has a shape of what I look at like as crutches or a funnel perhaps, centered at x equals h as an asymptote. So if I look at this, what I have is a vertical dilation factor of 2, and we've got an h value of -2, which means it moves 2 units to the left, and a k value of -3, which means it's gone down 3, which isn't really that much of a factor in log sketches. So what's our domain? Our domain is everything except for -2. So we say x is not equal to -2, or you can say with the backslash and then the curly brackets with a -2 there. The range is R, and hopefully you can see that because it goes all the way down and up again. So our rough sketch, the asymptote is a vertical one. That's because it's logarithmic. And the vertical asymptote is x equals -2. So we have a rough sketch of something like this so far. Actually, I forgot about the the vertical movement. So it's more likely to be shifted downwards by 3 units, so it might be perhaps something like this. So you have to be prepared for any eventuality. You're still going to get the same number of x-intercepts, 1 and 2, or 1 and 2, depending on the shape, and you're still going to get one y-intercept in either case. So let's see what we get. So let's find the y-intercept. To do this, we let x equal 0, and then work out what y is. So y equals 2 log to the base e of 0 plus 2 minus 3. So that equals 2 times log to the base e of the absolute value of 2, take 3. Now 2 is already positive, so you keep it as it is. So you have 2 log to the base e, of 2, take away 3 as your y-intercept. So you can write that in exact form as 0 to log e to take away 3. Or if you use a calculator, it's approximately equal to 0, -1.61 if you're writing it correct to 2 decimal places. Next we'll work out the x-intercepts, and to do that you let y equals 0 and then solve for x. So 0 equals 2 log to the base e of x plus 2 take away 3. And our first step is to get rid of the take away 3 by adding 3 to both sides. So that gives you 3 equals 2 log to the base e of x plus 2. We can then divide by 2, so you get 3 over 2 equals log to the base e of x plus 2 in absolute value terms. And then here we just use the same tricks as before. We have to raise everything to the power of e, so that becomes e to the power of 3 halves and leaves behind this absolute value thing. So what we have is e to the power of 3 on 2 equals the absolute value of x plus 2. So now we have two possible scenarios. Scenario 1 is where the absolute value of the contents of the absolute value are positive, and scenario 2 where the contents are negative. So we'll split them in half like so. Here we'll have if the contents of the absolute value are positive, then it equals to e to the power of 3 over 2 equals x plus 2. And if we solve that for x, we get x is equal to e to the power of 3 on 2 take away 2. That's the exact version. The approximate version you'd get from your calculator, which gives you 2.48. That's corrected 2 decimal places. Now this actually corresponds to x being greater than or equal to negative 2. So that actually matches, because 2.48 is bigger than negative 2. Now the second scenario is where the contents of the absolute value are negative. So we have if x plus 2 is less than 0, then e to the power of 3 on 2 is equal to the negative 1 times x plus 2. And that gives you negative x minus 2, which then you can solve for x by adding 2 to both sides. So you get e to the power of 3 on 2 plus 2 equals negative x. And then last but not least, you divide by negative 1. You could have divided by a negative 1 before, but I chose to do the expansion for some reason. Equally fine for both reasons. So that approximately equals negative 6.48 to 2 decimal places. So to clarify, if I was to look back here, this would give me x is less than negative 2. X is less than negative 2. Okay, and that makes sense. It matches up because negative 6.48 is indeed smaller than negative 2. So here's how I do my final sketch. I know that I have a shape something like this, and the asymptote is x is negative 2. What else do we know? And we know from previous work that the y-intercept is 0, negative 1.61 approximately, and the two x-intercepts are 2.480 and negative 6.480. So this helps me to draw my axes and therefore sketch my graph in the right spot. So here's the approximate version. My asymptote at x equals negative 2 is over here. And if I put my y-intercept in, it's going to be negative down here somewhere. And if I put my x-intercept of 2.48, it's going to be slightly over here like that. And negative 6 is way over off the scale somewhere. So something like this is good enough. It looks pretty bad actually, but I'm looking as a maths marker for whether you've put the labels in the right spot. So you go 0, negative 1.61, and this one will be 2.48, 0, and this one is negative 6.48, 0. Now, if for some reason you are not asked to round anything to any decimal places, then that means you have to put everything to exact form. Now that's a terrible line, but you get the idea that that's an asymptote, and I would pay that because I've labeled it. Okay, so that's the marking there. And I would be looking as a marker for whether you marked in your intercepts as coordinates. Now, if we're going to put in exact form, this one would have coordinates of 0, and what was it? 2 ln 2 take away 3. It's meant to be a minus. Okay. Now, this one over here, terrible arrow, but you get the idea, is going to have coordinates of e to the power of 3 on 2 take away 2, and then 0. And then last but not least, this one here will have coordinates of negative e to the power of 3 on 2 take away 2, comma 0. Where is it? Something